Okay, thank you, Tamer. All right, so then we can we go straight to the point. So we try to understand why it's so important to think about systems and systems behavior when we want to make decisions, predictions, when we want to understand what is happening, what's going on. Now, there are three things we do in science, but are essentially three things we do whenever we need to make decisions, address an issue. And these are explanation. Explanation within science is causal explanation, so cause-effect relationships that may explain a certain event or a certain behavior or system. And then there is prediction, so we want to predict things. And if you have a causal explanation, that usually helps predicting future events, not always, okay? But it does provide some good hints. And then we want to control phenomena. Okay, by control, we mean manage, for example, epidemics like COVID. We want to control and manage the fisheries. We want to control and manage, and so on. Okay, so by controlling, we mean intervene to obtain a certain outcome. And now, within this context and discourse, of course, the outcomes we want must be sustainable. So then we put constraints on how we can control the system. Okay, so now we can look at some systems, ecological, for example. That's a very old representation of an ecosystem. It was proposed by Lorenzo Camerano, who was an Italian marine biologist, who had read Darwin. And after reading the book, he was inspired to understand the ecology, so all the relationships between species and the ecosystem. So he had a very early food web representation in which all the links between species, the species are labeled, okay? All the links between species are representing either predation, so feeding links, or parasitic links. So this was a very early representation of predation and parasitism. And it already provided an idea of the complexity. At the time, we didn't have the tools to analyze, for example, complex networks, as the food web we're looking at is. And so for Lorenzo Camerano, it was a simple graphical representation that helped him at least to see the complexity of the system. Okay, so then now this idea of systems has been with us for a very long time. So social systems often were represented pictorially, so very, very many years ago already. So there were pictorial representations, graphical representations that were summarizing a bit what different people did in a community, so as to make sure that the society would function, right? And these were quite nicely summarized already back then. And then we have economic system. Here we have a slightly more modern representation of something that was already understood back in the early 1800s. So these are the system components, consumers, we have labor, we have nature with its resources and so on, and then you reconstruct the economic system with the flow of money through that system. And then finally, something more recent. This is the first representation of the Earth system. Okay, that's something. It's a diagram by Bretterton from 1986, which is very, very famous because it really captures in a simplified way what are some of the main concerns we have nowadays, for example, with climate change. Okay, so the CO2 now is part, for example, is an integrated part of the world system, and its levels, turns out, affect climate. Okay. Now, a system understanding showing the role of CO2, for example, in generating, for example, in causing a given climate response, those are crucial. So understanding the place of CO2 in that broader system, the Earth system, if you want, is crucial, and a systemic representation provides that insight, okay? Understanding why CO2 is important, why a given greenhouse gas might be important, okay? Okay, so the reason why decision makers, policy makers began to worry about and consider system thinking has been that whenever making decisions in the past without an insight into how does the system and making decisions about works have often resulted in very surprising outcomes that were not necessarily what the decision maker intended. Okay, so there have been surprising, in some cases, catastrophic outcomes simply due to the fact that you make a decision with a very simplified representation of your system in mind, and then because of some components had not been taken into consideration, the system just strikes back. So you get some strange effect. A classic one that is very famous is an operation done by the World Health Organization that was forced to parachute cats on an island, and the reason was that a given intervention with DBT on that island backfired, and there was something surprising emerging in that particular area. So the reason why the World Health Organization intervened in Borneo was that they needed to handle a serious malaria outbreak. Okay, so in that region there was a local community that was affected, very negatively affected by malaria. So the World Health Organization decided to go in and then spray DDT all over the places, and the idea was affect the vector of malaria, of course, the mosquitoes in that region. They did so. What happened was that eventually the spray on DDT resulted in an increasing number of rats on the island, and that eventually also brought a serious epidemic of pests. So a much more serious disease than the original epidemics of malaria. Okay, so the system backfires. The World Health Organization is confronted with something very serious. They find a simple solution. How do we control the number of rats? Well, we parachute the cats, and they did so, and that was, of course, a bit surprising for the locals. But the problem was to understand why the backfire. So why I suddenly get a sort of increase in rats on the island. So what the World Health Organization did was to think about the specific, so the component of a system they were familiar with. They knew that malaria had a vector, it was the mosquito, and they knew that DDT was an effective insecticide. So it helped control the numbers of the vector. Okay, what they didn't think about were the other component of the system. Okay, so on in the area that was treated, there were cockroaches that tolerated relatively high levels of DDT. So they were living with very, very high exposure, and they were eaten by geckos. We're very fond of these cockroaches. The geckos were again filled with DDT, and then eventually cats ate the geckos. And the level of DDTs were too high, so they died. Okay, so no one was eating the cats. What happened was that the cats there was a toxic response due to DDT. And then eventually, the lack of cats no longer controlled the rats numbers on the island. So the system representation, a simple system representation, would be something like this. So there are links, or if you want, arrows showing the causal relationship, the cause-effect relationship. So DDT affects somehow the mosquitoes, which again affect the malaria levels, but DDT can also affect or somehow affect the cockroaches, which affect the geckos, which affect the cats, which affect the rats on the island. Okay. Okay. Now, the problem that the World Health Organization experienced at the time was that they focused on they had a narrow focus. Okay, they were zooming in just one part of the situation of the problem and didn't thought more broadly. But they were used to think in systems terms. Okay, but most people that make decisions often don't do so. What we usually do, at least when we communicate, is to focus on events. Okay, so we are told that there is an increase in malaria, and then we think, okay, there can be different reasons for that. One possibility is that there is some type of relation, so there might be some change on the island, and knowing that the mosquito is a vector, you may be looking for increases in the vector numbers, right? So you may look for other events that may relate to the outbreak. Okay, that is the typical first approach, or at least when we communicate about a system and a problem, we speak of events. Okay. Now, when we start investigating a bit further, we look for actually patterns. So we look for correlation associations. For example, we look systematically higher numbers of mosquitoes, for example, that are vectors of malaria are associated with higher malaria, higher incidence of malaria, and so on. Okay, so we look for pattern typically in the data. We look for evidence, and that provides a better overview of what the state of the system might be, but it's still not telling us what the cause-effect relationships are, right? So once we have an idea of the patterns, we are better able to identify candidate relationships, so what type of cause-effect relationship there might be, and that is the systemic structure that we were missing here. Okay, so these cause-effect links that provide a systemic, so you have a wall, if you want, of connected components, and then we immediately understand that any intervention has implication not only for a target, for example, the mosquito, but also for other components in the system. The effects can be direct. DDT directly affects both mosquitoes and cockroaches, so insects, but there are also indirect effects mediated by those components. Okay. Okay, so the typical, this iceberg idea of the lack of system thinking, okay, is stresses the fact that if we only focus on events, we miss the parts of the system and we don't have an understanding of the system. If we move over to patterns, try to find relationship out there based on associations, we have a partial understanding of the system, but we cannot distinguish, for example, the differences between direct effects, indirect effects, loops, or also feedback loops, and so forth. It is only when we have the systemic representation that we can start reasoning about, for example, intervention, prediction, causal understanding. Okay, that's it. All right. So the idea then is that we do need to think in systems because all system components have strings attached. So they have links, so cause-effect relationship with other components of the system. And then the challenge becomes to identify a sufficient, so a system with a sufficient number of components to be able to predict the behavior of the system. For example, if I'm planning an intervention, so I'm making decisions and I want to change something in the system. I want to know the implications, and then I need to know what the system comprises, okay? And what the system looks like. Okay, so that's the why. So why we need to think in terms of system, so systemic thinking. Now we can try to understand a bit what that means, really. So we look into the relationships and the effects. I'm probably pretty loud, so I may want to close the door. All right, so we can start with a very simple situation, okay? We try to understand why would the World Health Organization spray DDT, which affect insects, if the target was the malaria, okay? So what is the thinking that the World Organization was making, okay? So here we have a simple system. There are different components here. I can break down that system into the direct effects, okay? Just focus on direct cause-effect relationships. And there are two such relationships. There's one relationship that shows how the DDT itself that is being sprayed affects the mosquitoes, and the effect is negative. So there is a reduction, an expected reduction in the number of mosquitoes as an effect of the DDT spray. And then we have the positive effect of a vector on the spread of a given disease. Okay, so if there are more of the vector, we get more malaria in the area. Okay, so that was a simple decomposition of that causal chain that we were looking at. It is simple. The idea, these are qualitative representations. So the only thing I want to predict is whether the effects are negative or positive. Okay, I don't know by how much malaria increases with an increase in mosquito numbers. I just want to know the sign of the change, okay? So that's simple. But what about the indirect effect? Okay, so we're looking at direct effects. These are easy to understand. DDT affect negatively mosquitoes, mosquito affect positively malaria. But if the question is really, how does DDT then affect malaria indirectly? Okay, you might be familiar with this type of calculation, computations. What is your guess? Does DDT have a positive or negative effect on malaria indirectly? given the causal chain, negative, positive. Yeah? Okay, it's negative. Why is it negative? And by why I think, okay, if I have the information about a chain of a negative and a positive effect, how do I compute the negative from those two? It's something, if you're not familiar with how you do indirect effects computation of the signs, you can guess it from your math. Usually, if you multiply signs, so -1 multiplied by +1 would be -1, right? So if it's that simple, what we need to do along chains of cause effects or causal pathways, as they're called, we just need to remember to multiply the signs to get the final indirect effects of any components. For example, DDT, its indirect effect on the target component we are thinking about. Okay, so that's super easy. Okay, this is something we can do without advanced computation or simulation or anything. Okay, so that's all they were thinking. So the World Health Organization was thinking about the negative indirect effects of DDT on malaria, and they had a simple representation in mind. And that representation, by analogy, can be transferred to other systems. So that's one of the big advantages of system thinking. You can, by analogy, once you've solved a given issue in one system, if you find a different system with a similar structural representation, for example, this system here, you can somehow inherit the insights from the previous analysis and apply them here. Here is again a situation in which DDT comes in handy. Back in the days, pest control in agriculture, and I'm thinking the 50s, was sort of a boost for the chemical industry. So the DDT became very widespread. It was used in many settings, including situations in which you had a natural enemy or your pest in the area, okay? But the target, the focus of the industry and the policymakers at the time was to affect the pest to release the plants from the damage, so as to promote the agriculture and production. Okay. Now the problem was that much of the focus was ignoring the natural enemy. Okay, so they were spraying DDT, thinking of one target. Okay, the pest, ignoring the ecology. Okay, and just focusing on the effect of the pest on the plant. Okay, now the effect of the natural enemy on the plant, you have learned to compute. Okay, so in this case, what is the effect of the natural enemy of the pest on the plants? If you help me, I can go.
Mm-hmm. It's positive. It's like the principle: the enemy of my enemy is my ally.
Yeah. Spot on. Okay, so that's the thing. You have natural enemies out there, and it's probably not a good idea to target those with an insecticide. Okay, so thanks. Okay, so it's a plus. We know how to reason now. We have that simple tool to deal with indirect effects and these causal chains, right? So that's what people did at the time. They were spraying DDT and without thinking too much about the whole system. They only thought about the simple direct relationship, and that possibly was not a good idea. So there was a scientist, an ecologist, who was also working with applied issues in agriculture, for example, Richard Levins, who was a theoretician, and he understood causal, also system thinking very well. So and we're back in the early 60s, what Richard Levins was proposing was that perhaps spraying DDT, without just think about the pest target, but thinking a bit more broadly about the ecology, wasn't such a good idea. Okay, so he was saying that essentially, if you spray DDT and you target both your pest but also the natural enemy, you may get undesired effects. Okay. All right. So now we need to try to understand what Richard Levins was thinking when he said that. Okay. So, all right, then we need to remember what the World Health Organization did wrong. Okay, so we learned from the previous example was that if you consider single targets, for example, only the pest in your interventions, that's not a good idea. So now we have the full representation with the DDT targeting two components of the system. Okay, so those are the direct targets of DDT intervention here. That's good. Okay, and then the other thing we need to remember that the example with the World Health Organization helped us understand is that it's not sufficient to focus on direct effects. We cannot just look at the direct effects of DDT on a target and non-target species. We need to think also possible indirect effects, so more complicated causal relationship. Okay. Okay, so the more demanding question to us right now is who suffers most from DDT spraying? The pest, which is our target, or the natural enemy of the pest, which is our friend, right? As you were saying. Okay. All right, so who is suffering most from DDT? Is it the natural enemy, who is our friend, when we want to produce wheat, for example, or the pest? What do you think? And by who is suffering most, probably we're thinking who is receiving more negative causal effects, right? Either direct or indirect. That's what we're thinking about. So as you see, I'm not thinking quantitative. I'm not asking by how much will for example, the natural enemy suffer, but just whether it's suffering more. So whether it's experiencing more negative effects. Okay. Now, if you represent the system in word, also for the final target of the decision makers, this may make life a bit harder when you want to answer a specific question like this. Okay, so one way of simplifying a bit is to remove what is not relevant here. So I'm asking who suffers most from DDT, this parasitoid on top or the pest. I can remove the wheat and the indirect effect and just focus on what matters. Okay, so who is suffering most? We can start from the parasitoid. So we see that there is a direct negative effect of DDT on the parasitoid. Okay, and then there is a negative indirect effect through the pest to the parasitoid. Okay, so I see that there is a direct negative effect here, and this effect I see it's negative times positive, it's negative. So the parasitoid is receiving two negative input. Okay. Now, if we do the opposite, we look at the DDT effects, the indirect effect on the pest, it's negative times negative, that's positive. And then the direct effect, it's negative. So the pest doesn't seem to do too poorly when we spray the DDT because the pest is being released of its natural enemy. That was the simple thinking. And that's all it was necessary to understand that maybe biological ways, for example, of increasing production using natural enemies could be more efficient than just spraying DDT, for example. And that was what Richard Levins tried to push. Richard Levins at the same time was developing many of the tools we use today, loop analysis and other methods, to handle the complexities of the ecological systems for which we want to make decisions. Okay? Okay. Now, new analogy that's quite similar. I mean, we have a natural enemy, cod, capelin. We have the prey of capelin, so zooplankton in this case. And now we are targeting cod and capelin through fisheries. Okay, so it's all done by analogy. Now we're using the same thinking all the way. It's super easy when we can do it this way. Now remember that we have already done the selection of the components, reconstructing the causal relationship. So it's super easy because the systemic thinking already has happened. And the question now would be very, in a way, akin to the previous problem. The question is whether I have a combined fishery on both cod and capelin. Is that a good idea? It's for example, having fisheries on both cod and capelin. Is the coexistence of those fisheries going to work well? Are there trade-offs? Are there problems emerging from combining fisheries on a top predator, for example, and its intermediate consumer? Okay, these are the general questions that are addressed by fishery managers. Okay, now fishery managers historically have focused on a target species and the possible direct influence of fisheries. So historically, much of the focus in assessment and fishery management was on single components. Okay, specific components. So in this case, cod, for example, that was the target of the fishery manager decisions. And what they wanted to know was how is the recruitment of cod going? They used short-term, for example, data from last year to inform what the recruitment this year might be. And then in light of information on the cod, they could make decisions about, for example, the quotas, okay, for the how much could be caught. Now, the problem is that right now, for example, there is a recruitment failure that, so essentially the new recruits of cod that were supposed to replenish the Bering Sea, for example, we caught in the future years so that the fishery could thrive and we would have a sustainable situation. That recruitment has been failing for 10 years in a row. So the recruitment of cod has been going down systematically every year, and they could not find a solution if you only focus on cod. Okay, so this is coming from Fishery Directorate, so people that are the policymaker here. The decision maker and the management, they are saying that the single system of this simple cod focus, for example, is really not helping at the moment to resolve why cod is in trouble. Okay, so they understand that now you need to expand a bit your perspective and include other components of the ecosystem, for example, and they fear and imagine that possibly climate change has a role to play. So there are changes ongoing in these areas that are driven by climate and that are affecting them indirectly cod through its recruitment failure, essentially. Okay, that's the situation. Okay, so what we do now is to expand a little bit. So we include one prey of cod and then its own prey, and see whether we can reason effectively. Okay, so find out whether combined fisheries on cod and capelin are good areas. Okay, so now we learned the approach. We need to account for all the relevant effects, the direct and indirect one, and then we can try to answer questions such as will harvesting capelin affect the cod stock negatively or positively? Okay, now I'll let you answer. You have the tools, you know how to do it. So how is harvesting of capelin, if I fish out capelin, how is that affecting cod, positively or negatively? Okay, so you remember, so the sign is attached to the, there's a cause-effect relationship, and the sign it's that matters is the one that is closest to the target. Okay, so the fisher has a negative effect on capelin. Capelin has a positive effect on cod. So the effect of fishery on cod, fishery of capelin on cod, the indirect effect, it's positive or negative?
Negative.
Yeah.
So cods are affected negatively by fishery directly,
yeah,
and indirectly through capelin.
That's very good. So we learned that lesson from Levin's back in the early 60s. We can apply it straight away, right? So that's super easy. Okay, so what about the effect of cod harvesting on capelin stock? Okay, so you're targeting cod. What is the effect on capelin? It's a negative times negative. So you are releasing capelin for a natural enemy, like the DDT was doing the parasitoid for the pest. So capelin actually is released of predation. So the numbers of capelin or the growth of the population, and in fact, benefit from harvesting cod. Okay, so that's the other side of the medal. And then finally, who suffers most from both fisheries? And you already provide the answer. So that insight, right? So the cod suffers most from two fisheries, one on cod and one capelin, because there are two negative effects, one direct and one indirect through capelin on cod. That's how simple it is. And incredibly, also fishery management in the past didn't do multi-species consideration. Okay, so very simple representation, very simple reasoning, qualitative reasoning, and we see the challenges, right? The problems of having combined fisheries in an area. But if we simplify a bit, right? You remember, if we remove some of the complexities and target, so focus the components that are relevant to the specific questions, we can make life easier for us. Okay, so you have a system representation, and then when you have the specific question, you target whatever component is relevant for you. Okay, so this is now something we are accustomed to. We can answer rather complicated questions. So the combined fisheries, what they do to our system. So we're getting very, very much experience already, okay? Okay. So to summarize a bit, system thinking then, it's really about identifying all the relevant targets of the direct effects of a decision. So you reconstruct the structure, the causal structure in the system with those arrows and signs for the negative or positive effects. And you want to identify the relevant targets for your decisions, for example, whether to harvest or not, whether to spray DDT or not, okay? And then you want to account for the size of all direct and indirect effects of a decision affecting a target component of interest, okay? So that's it, all right? So up to now, things are relatively simple. And the reason is that we are focusing on essentially on causal structures, if you want, on cause-effect relationships that are amenable, so they're open to relatively simple solutions, just this keeping record of the signs, right? The direct and indirect signs, and we can think of summarizing that in a table. For example, you could have the different components of interest in a what are called adjacency tables or matrices, and you just can plug in all the plus and minuses of relevance, so you can see whether affecting a given target or given component of the system has positive or negative effects on everything else. And this type of summary tables are quite common, very easy to produce in relatively for simple systems, much more complicated for complex systems, and we'll see why when we start talking about feedback. Okay. Okay. All right. So now, direct and indirect relationship between system components may generate trade-offs and introduce feedback. Okay. Now, the trade-off we have here is between the cod and capelin fisheries. So if it turns out that there is for the cod fishery, that there is a negative effect of the capelin fisheries, the responsible for the cod fisheries, which might be a different group than the capelin fisheries industry, they may realize that they don't want to have too much capelin fisheries in the area. Okay, so they have a negative effect of that, and so they may actually question whether it's a good idea to have, for example, an increase of the quota of capelin in a given area. So that would be a possible case in which there is a negative effect of the one on the other. The capelin fishery says that, well, they should just fish the cod, all the cod they want. No problem, just, empty the system of cod. So they're not experiencing a negative effect of the cod fishery. So in this case, it's not apparent that there is a trade-off, right, between the two fisheries. But there are other situations in which both sectors, both parts, experience negative effects of the resource exploitation by the other sector or industry or part. And that causes this type of trade-offs that we'll be discussing in a few minutes. Now, the other thing that happens in this type of in any system, right? For example, ecological or socio-ecological that we may be thinking about, is that you may have what is called feedback. So what may happen as time runs is that if cod numbers increase, the number of capelin prey decrease because of predation, okay? These numbers become lower, so there is less of that positive effect, okay? There is less of less food for the cod, and less food is really a bad thing, okay? So the causal relationship we're thinking about of cod on itself, if you want, is to reduce capelin numbers and therefore reduce the food that comes back to the cod. So it's negative times positive, it's a negative effect, okay? And because the component of the system is influencing the effect itself, if you want, okay, on the rate of growth, we have what is called a feedback, okay? And the kind of this particular feedback, it's called a negative feedback, okay? And the effects of negative feedbacks in general are to balance or regulate the numbers of the cod, okay? And the capelin experiences something similar. If its numbers increase, the number of code increase. And so there will be more predators keeping the numbers in check. Okay, so this is a situation in which the feedback loop, as it's called, there is a looping, a cycle, if you want, looping structure. Because the feedback is negative, the effect is to keep the numbers in balance. Okay, so that neither code nor the Kepler can increase without check. Okay, so negative feedback has this nice regulatory balancing effect on the system. Nice. Well, it depends on what we are dealing with. And then there's a different type of feedback which is positive. If you have positive feedback, you tend to have an explosive effect. So it tends to promote a further increase in numbers, for example, of code. Okay, so the standard positive effect, so the positive feedback in population dynamics in demography is that the more animals you have, the more offspring you have, and then you tend to have a sort of escalating effect. So positive feedback and negative feedback are the two types of feedback you might expect. What complicates matters in a slightly more complicated representation than this is that there are many such feedback loops. Okay, and when there are many feedback loops, it is no longer the simple causal pathways that need to be focused on. Okay, the exercise we learn in just a few minutes. We need to think of the loop, this feedback loop structure, how the combination of feedback loops together drives the behavior of the system. Okay, that's slightly more complicated. It has with system dynamics to do, and that's topic for after break. Okay. Okay, so that's the last point. So direct and indirect relationship between system components may generate trade-offs. They may introduce feedback. We've seen how that might happen with this simplified system. Now we'll move during the second hour on, we'll talk a bit more about trade-off and feedback, then into system dynamics, and then we'll move into complex systems. So how to handle more complicated systems than this very simplified situation. Yeah. Okay. All right. So that's where we are aiming at. This is the type of complexity you may imagine you have in real systems. Okay. All right. So any comments or questions up to now? It's the pace okay? Is the speed all right? Okay. This is the first hour on a Monday at 8:15. So I'm taking that into account. We take, I think you usually have 15 minutes. 8:15. Okay. So we meet at 8:15. Okay. Yeah. It's yeah. And we start rental because it's tough in the morning. But yeah, I mean, these are things that everybody's familiar with it and has a notion or an intuition about these perspectives, and then it's fun to start using them. Yeah. Really. It's I think the most important thing is to find ways of actually applying these systemic approaches.
We come to that now in the next.
Yeah, so we'll show examples. What we've done now is to start with simple examples, see how we can apply this. And you were doing all the causal pathways already. So, and now we'll see a few more applications and then move into the more complex type of systems that eventually we'll have to confront. And so this is sort of introductory to that. But then as soon as you are dealing with this type of problem systems that are a bit more complicated, it's a good idea to train, to reconstruct. So we often draw conceptual diagrams of pretty much anything.
Yeah.
And it's a way of getting your assumptions on paper so that they're shared and discussed. And as soon as you do it, all these insights that you get from system thinking emerge. It's a good practice.
Okay, it will be harder to work with systems this big.
Yeah, so I'll show what the challenge. So when you scale up to stuff like that and see lots of species and so on, we'll see what tools. So it's I'll say a little bit about that. But then if anyone is interested, there is more.
Because yeah, working like this is what you have to do when it's like sustainability budgets, right? Like when you're trying to look at
very quickly, you have to down complexity and also scale, right? You move into large areas, and so that's where in a way we'll discuss. But the simple examples like the DDT example, spray and just go forget about any consequence, we just create wildly. Well, it doesn't necessarily help with the production to begin with. So even the local scale perspective helps. But in other situations, you need to have the inclusive large scale to see the challenges. Yeah. So Scott, we're looking a bit.
Taking time to put down.
They want the picture. He's so Brazilian.
Like the usual Twinings green tea. Yeah. I mean, like green tea in the morning is the thing that gives you like a bit of a push. The thing that's yeah. But I don't like it. I don't like it too warm.
He's not Brazilian, man.
I have like a cat stuff.
Oh, okay. So 60 degrees is more than enough, I guess. God.
Yeah, even a bit lower than for some reason. Like
No,
it's
sorry, nothing.
warm.
Then I will.
My tongue gets.
I don't feel. I find my football.
I need some caffeine. Yes.
I got this.
No, the eight.
Okay, I think we can start.
I mean mocha. Okay. Then we are talking about coffee.
Okay. All right, so everybody's back very soon. Okay. Okay, so we said trade-offs and feedback. Now we start touching on feedback. That invites us then to think about system dynamics and what are the dynamic or the system behavior implications of the structures where reconstruct those cause-effect relationships we are reconstructing. And then we'll move into tools to help us with complex system thinking. Okay. All right. So that's what we close on. Yeah, I think I'll this. Keep it inside the room. So direct and indirect relationship between system components may generate trade-offs and introduce feedback. Okay. So when we reconstruct all those with those arrows, right, and signs, we may find out that a trade-off, for example, between different industries or sector may emerge. So a trade-off is defined loosely as any situation where making one choice to obtain something means losing something else. Okay, so it could be that one sector needs to decide what to focus on, code or catering, for example. It could be two sectors we mentioned, oil and gas, industry, and harvesting, deciding which area they should operate. Okay, so all these are situations in which trade-offs may emerge. And the idea is that trade-off is you can't have your cake and eat it, right? So due to a trade-off, you either choose to have the cake or to eat it, or a compromise. Okay, so that's very intuitive. What is interesting is that typically when a trade-off emerges, the only thing you can do is to manage it. Okay, so you don't solve trade-offs. It's a general insight from management, from say spatial planning. We mentioned the Bering Sea case. Different sectors there need to coexist. You need to manage their activities to ensure that trade-offs don't cause big implications to the individual sector. Okay, so we manage trade-offs. Okay, all right. So now the first intuition: is there a trade-off? In this case, we have the fisheries on two target species. Is there a possible trade-off between them? If there are no connections between either direct or indirect between the two stocks, then there is not necessarily a trade-off. Okay, so that's something that just to help us see possible candidate pathways that cause trade-offs. Okay. Okay, so that's a simple intuition. Now, the other topic we wanted to introduce are feedback, and we started looking to a feedback. I gave it like a very short intro to the called Kaplan type of feedback, so a predator-prey negative feedback loop. Now, the definition is a bit awkward. So feedback is the influence of an effect on the process giving rise to it. All right, whatever that means. I think using examples will make things clearer, but why should we care? Because the feedbacks, they actually influence the behavior of a system, so the dynamics of a system. Okay, so if you want to think in terms of sustainability, and you want to maintain, for example, the abundance of different species, positive and sufficiently high, well, dealing with that requires a perspective on system dynamic or the behavior of the system. So the number of species fluctuate through time, and we want to understand how they do so and what happens to the numbers if we make an intervention. For example, we start fishing or stop fishing in an area and so forth. Okay, so the feedback for the codon capri we have seen. So we have this is a classic in ecological theory. So there is a predation of codon capri. So we have negative feedback. So we need to look at the indirect effect of cod on itself, okay, and the indirect effect of capelin on itself. They're both negative, okay, and then there is negative feedback, which typically balances or regulates numbers, so keeps numbers in check. That's what negative feedback does. Positive feedback, if you have that, you will tend to have increasing numbers of whatever system component you're focusing on affected by the positive feedback. Okay, so that's it. These ideas of looking at direct and indirect effects and their implication for feedbacks, for trade-offs, and so on, have been understood in ecology for a long time. So Darwin started very early with an example and said, more cats, more clovers, okay? And he had a slightly more advanced, so there were 4 components here. It was a slightly more advanced example than the ones we have covered earlier on today. So we have a negative effect of cats on mice, which eat the larvae of bumblebees, which pollinate. And here we have a positive effect on clovers. So the effect of cats on the bumblebee is positive, and its own effect on the clover is positive. So the indirect effect of cats on clovers is positive. And what Darwin said back then was more cats, more clovers. Okay? So he was thinking indirect effects. Okay? So this intuition has been with us for a long time. What is less easy is increasing complexity of systems, feedback loops that influence the different system components, more interventions, so more effects. We're talking about cumulative effects and different sectors operating in an area and impacting the system from different angles. Those are the complexities we need to deal with today to tackle, let's say, real-world situation in which we need to find good decisions that are sustainable. Okay, so system dynamics is the underlying idea. So the behavior of the system, the number of cods, for example, and capri you have out there, they depend on inherent behavior of the system, and then your intervention will impact in a certain way depending on the causal structure of that system. Okay, so we have learned that feedback is crucial. So feedback really decides the rate of change of the system for the different populations of interest or different properties we're interested in. We have defined negative feedback, the diminution or counteraction of an effect by its own influence on the process giving rise to it. The positive effect, the enhancing or amplification of an effect by its own influence on the process. So the definition is almost longer than just providing the example and getting the point. The last thing we need to think about is that there can be feedback of codon itself that are population level. So they don't need to involve other components of a system. But as soon as you have multiple components, you can generate these loops, okay? And those looping structures can involve a chain of many components and then get back to the start. And of course, the longer the chain, so the longer the loop, the more the components along that loop, feedback loop, the more difficult it is to be aware that there is a loop in the system, okay? and then the effects of those loops are more demanding to study. Okay, to make things a bit short with regard to behavior, also dynamic implication, negative feedback balances numbers, okay, properties, and positive feedback reinforces. So we get runaway effects or explosive increase. Now, another insight that came in very early from the mathematical study of system dynamics was that if you have lagged feedback, so if it takes a bit of time for the effects of code on Kepling to strike back, okay, if it takes some time for feedback to operate, this lag destabilizes, for example, the number of code, okay? So it tends to destabilize and generate fluctuations. This can be small regular fluctuations that we can cope with, or could be very erratic. So we could have, for example, chaotic behavior, which is very difficult to predict. And so we need to understand what type of dynamic behavior are we dealing with. Just remember that lagging, so lag or delays in negative feedback tend to destabilize and generate fluctuation. And then generally, positive feedback tends to reinforce. So if the number are increasing and there is positive feedback, the number of code will increase even faster. And if we have a complex system, then depending on the certain ingredients, you may have also alternative equilibria, so tipping points in the system. And positive feedback is one of the required ingredients to have tipping point. Okay? So these are super general type of insights. So we need to remember there are two types of feedbacks. One balances things, keeps numbers in check. The other tends to make numbers explode. Okay? And then we remember that, for example, delays in feedback may destabilize, and that may matter for our problem attempt. Now, the good thing about system dynamics is that if we forget for a moment the mathematical complication, the implications, okay, the dynamic implications of different type of feedback structure you may have in your system, well, there are only four. So there are four dynamic possibilities at equilibrium. So there is a system that develops in time, it approaches an equilibrium state, and you have only four options for what, for example, the number of code can do. They can be either in a stable equilibrium, so then we are in this situation. Okay, so we could have a triangle. Okay, so the code, the beard, and then there's okay, the number of code could either reach an equilibrium and then stay there, and then there are just small fluctuations due to environmental perturbation, so just stochastic variation, so underlying variation that we don't care about. The equilibrium is stable. The other possibility is that, for example, code engages with Kepling into a predator-prey dynamic, so a couple system of code and Kepling. Their numbers are linked, coupled into a negative feedback loop. There is a delay, it takes time before the numbers, the increasing number of Kepling, for example, have an effect on the numbers of code. There's a lag, and that destabilizes. So suddenly, code fluctuates in the system. And then, if I see that, also the first case, it's simple. I see that numbers of code are stabilized, so I know, okay, there's a negative feedback in the system that keeps the number in check. Okay, I see it just by looking at the long-term behavior of the system. Now, the second situation, what it requires when I see a regular fluctuation is to find where the lag, the delay in the negative feedback might be. Okay, so I know already when I see an unstable situation, I know already what to ask. So I know where to look in the system stuff. Then there are slightly more complicated situations with so-called quasi-periodic situations. These are a bit more irregular. Okay. Yes. Okay, they're a bit more irregular. And then there's the chaotic behavior that looks very erratic. Okay, so these are particularly difficult to spot, stuff like that. Now, for a number of ecological systems, we have seen that the chaotic behavior can actually be in place. And what we need to remember for this type of complicated chaotic behavior is that you need at least 3 system components or more in order to generate this type of complicated behavior. So typically is an interplay between more variables, more species, for example, in an ecosystem. That's the one thing. The other thing to remember is that this type of behavior, which requires serious delays, for example, in the feedback loops, negative feedback, it's very sensitive to initial conditions, which means that prediction becomes difficult, okay? So I need to have a very precise idea of what the numbers of code are at this precise moment if I want to have any chance to predict where the numbers will be next year. Whereas in these situations, the predictions are much easier, okay? So if we have a system that has this type of chaotic erratic behavior, the challenge is the prediction. Okay, so you need to keep up with the numbers all the time. You need to monitor constantly to know what to expect next year, for example. Okay, that's it. There are 4 possibilities at equilibrium, but nothing impedes a system from having more than one equilibrium. Okay, so you could have, for example, a situation in which for a given system, for example, code could reach either low equilibrium number or high equilibrium number. So in this case, we have 2 equilibria, same population, same system, 2 alternative equilibria. And what separates the 2 is that tipping point we're talking about, okay? So there's a line, and if the fisheries, for example, push the code numbers below that line, this is an unstable critical threshold, then the code eventually reaches the low equilibrium. And if for some reason numbers increase beyond a certain point, the code numbers will end up at that higher equilibrium. Okay, so this type of alternative equilibria in complex systems are quite or can be expected or quite common. So in ecosystems, we often think if I have a superficially complex ecosystem, I probably can expect that it's so-called metastable. So there are alternative equilibria, alternative state for this system that I need to have some insight in, or at least I need to know whether there is a risk of a critical threshold which suddenly generates this type of regime shifts or critical changes in the system. Okay, so that's it. So just 1 slide, 2 slides on system dynamics. That's not much, but it gives a flavor, right, of the type of things we need to remember when we think about behavioral systems, what features we need to consider. Okay, you always notice that I try to attach something. So stable equilibria, you need negative feedback. Fluctuations of any type, you need a delay. So I need to simplify a bit and think what is necessary to generate the different behaviors. And once I know that, I can look for causes. Okay, I look at the system and I try to find the delay. I need to find the feedback loops and so on. That's how we proceed. Okay. All right. Okay, then resilience in this setting, it's often used as a property for ecosystem and so on. It's a problematic term because it has different authors have interpreted resilience in different ways. Holling, who proposed it as an ecologist to begin with, was thinking about this so-called return tendency of the system. So how quickly, for example, the numbers of code can return to an equilibrium. So if I disturb per turn, how quickly code returns back to its equilibrium state, and that time is a measure of resilience. The quicker, the higher the resilience. So the greater the capacity to withstand perturbation by the code, for example. Okay, so these notions are important. They can be answered by looking at the system or models of your system. You can reconstruct what is this return tendency, whether it's high or low, and you can even reconstruct what causes, for example, low or high resilience in a system. One reason could be the parameters of the system. So it could be something about, for example, the birth rate of code. So there can be properties of the code itself. Okay, but there are properties of the system that can generate higher or lower resilience as well. So all those feedback loops we've been discussing up to now. All right. Okay, so now we go into the more complex situation. So we have kept it simple up to now. Now we're going to tools for system thinking that helps us cope with the complexity of the type of systems we're looking at. Here's one example, the Bering Sea ecosystem. There are many species in there. human activities, they include harvesting, but there is the oil and gas sector, shipping and noise, so tourism and so forth. Oil and gas extraction. So there are many, many perturbations of the system due to human activities. There are many components of the Barents Sea, to the Barents Sea ecosystem. So how can we simplify and represent in a useful way such a system? Okay, that's it. Now we're going to touch on quickly on the full complexity. So we look at situations in which you have multiple, so different human activities that you want to manage or you want to ensure are sustainably operating within a given area, for example. So here we are in the north. We can think this is the Barents Sea, and there is commercial fishing, oil and gas, shipping, and so forth. Okay, many activities, and then we have the ecosystem, and there are different components to the ecosystem. Now, when the different sectors usually look into the system, what they think about are the components themselves. Okay, so they typically think, am I affected, for example, is I don't know, fisheries affecting some non-target species? Okay, so bycatch. Well, that's something they focus on. That's a direct effect. It's shown in blue here. Okay, blue arrow. The same happens when there are two sectors discussing whether they might have synergy. So effects that together, there is a cumulative effect of the two sectors that could be, for example, interactive. So they amplify each other impact on a species. That's again focusing on direct effects. But what we have seen today is that when you look at systems, direct effects are not enough, right? So we've seen that there are further causal links within an ecosystem that may, for example, spread an impact further into the food web, for example. Okay, so we need to account for all the relevant links, and these are typically ignored. So what happens beyond a given target species, it's often ignored by managers and different sectors operating, say, in the Barents Sea. What our role has been, so as scientists, has been to make sure that the causal structure, the system structure, emerges through research in a way, and that the relevant links become apparent, and that possible changes in the causal structure that is, in this case, purely ecological, for example, so the food web structure, for example, changes in the food web structure in the system itself due to, say, climate change, become immediately available to decision makers so that they are aware that they're no longer harvesting in the same type of ecosystem. Okay, that's the type of work for example, we have contributed to. So looking at the causal structure, looking at the food web structure, showing that it has changed, that the implications of harvesting or cumulative risk, the implications for cumulative risk have changed. Okay, these are often dealing with indirect effects of individual activity. Okay, so we can start simple again. We have something a bit more complicated as a sort of simple representation, and it's an example. That's a representation that has been used in management when doing multi-species type of considerations. We are focusing now now we're going to simplify. We look into some of the main target prey for the different components of the system and predators. Okay, this could be such a representation. And then we could ask, okay, by looking just at direct effects, very, very simple representation, what is the impact of fishery or cod fishery on other members of the food web? Okay, and so of course, these are negative effects, you know, anything moving from cod to its predators are negative indirect effects, and anything going down to prey of cod will be positive. On capelin, we've learned already, but for example, for I don't know, an amphipod and for shrimp or krill, the effect again is indirect effect of fisheries on cod can be positive. Okay, now this is a simple representation. You can reconstruct very quickly all those effects of fisheries mediated by direct effects on that link cod to predators and prey. But if you add some of the realism, so you Minke whale doesn't feed on cod alone, but also on capelin. It can even feed on some of the invertebrates. When you add realism, the situation becomes immediately a bit more complicated. And if you want to include direct and indirect effects in your considerations, you end up in this type of loops. So you look, for example, the effects of fission and cod and its spray, which again affects feel, which in itself affects code, and so on. So the loop instruction pop up as soon as you add some realism to your presentation. So you need to cope with that. Now, at present, the institution that does supposed to help with managing stocks and managing ecosystem more recently is ICES. And what ICES presents for the different large marine ecosystems in our area is something like this. So what ICES has been developing are these ecosystem overviews, okay? And as you see, they are already, they have some level of complexity, but in fact, they are very, very much aggregate and simplified. So they cannot, by their nature, they cannot provide an idea of the indirect effects we're talking about, okay? So what you can look into when you look at the ecosystem overview from ICES for the Barents Sea, for example, are the impact pathways, okay? So fishing has an effect, which is a selective extraction of species, which itself impacts fish, okay? So we have a causal pathway from fishing to fish species. That's intuitive, okay? But there are other effects, for example, trawling as an abrasion on the bottom habitat. So the trawls affect mechanically that bottom habitat, and that affects benthos and fish, okay? So there are a number of such causal pathway that we can follow. These are non-looping structures. There is no loop here in this representation. We have what is essentially a branching tree, okay? So it's a simple causal pathways that can be followed to see what impacts different sectors might have cumulatively on different components of the ecosystem. But the ecosystem components are so aggregate, all seabirds, all marine mammals, all fish, that we understand immediately the realism of the ecological system is lost, okay? You aggregate to provide an overview, but then it's very difficult to be sure that interventions that use this representation don't go wrong, okay? So what needs to be done? You need the summary, you need the summaries for policymakers and decision makers that can be simple representation like that, but you also need that realism we were talking about and understanding of the loops and the feedback loops in the system that affect their behavior and so forth, okay? So some level of, so you need to add some complexity to the simple mapping that it's being used at the moment for risk analysis. That's what it is, okay? And one possibility is to have network representation of your system. For example, in this case, we have an area out at sea. We represent the food web. We just, I think, changed the direction of the arrow. This is going from the prey to the predator, okay? So we have a simple representation of the ecological system. Then we have a social network representation. So we have this would be a web, a food web, if you want. This is a social network showing the relationship between, for example, conservation needs, tourism, banking, shops and markets. And then we have offshore wind parks, okay? So the offshore wind park, the decision on where to place them, when to place them where, is the particular decision that the paper dealing with this example was addressing. And we see already that the wind park has implication for the socioeconomic system of a given area and might have at least indirect effects on some of the species as well. So the challenge here is to combine the insights on how the ecological system works with the insights from the socio-logical system into one representation. If that is possible, and if we have the sufficient insight to produce this type of connected, so combined socio-ecological representation, then by keeping that idea of positive and negative, here we have positive arrows. So these are showing the positive effects, and the circles are showing the negative effects, for example. So by representing all the direct effects, we also eventually obtain the indirect, possible indirect effects of those causal relationships, and we have the feedback loops in the system. Now, that's a qualitative representation. We don't have the strength of the effect, so we don't know by how much the wind park affects a given species, positively, for example. We don't know how strong that effect is. We just have the qualitative representation. And just based on a qualitative representation, via a so-called loop analysis, we can look into the expected effects of the different, of perturbations on the different component, okay? So we can then ask if I, for example, increase the offshore wind park sector, if I increase it, which components might be affected? Okay, so if I have a perturbation on the offshore wind park, which components of that simple representation are affected negatively in red or positively in blue? So you have the full story, and then you can look at any perturbations of any system components and summarize it with this simple heat map, for example. Okay, so that's we are still within manageable complexity. This type of tools you can use up to 20, 25, maybe if you stretch it, nodes, so different system components, to simplify and represent something very complicated. Okay. Now, for that representation, you can keep the qualitative representation and then study the implications. And there are tools to do that. This loop analysis tool can do it for all. Okay. Okay. So these are qualitative models that help us understand. All right. So now we need to think, what about further complexity? So if we're moving into very complex representations of the reality of what's going on out there in the Barents Sea, for example, what needs to be added to the intuitions about direct effects, indirect effects, loops that are negative feedback or positive feedback loop? So is there something else we need to use to address that complexity? And that's very important because complex system thinking it's what is needed pretty much for many of the realities of, for example, sustainability challenges. So complex systems have many interrelated components by definition, determining feedback loops and multiple pathways of indirect effects. That's the complexity. Okay. So if I have a perturbation of any component, I can expect that implications can be there for many, many parts of the system. So I need to be aware of this candidate indirect effects of a intervention. So some activity, a management decision, for example. Okay, so the complexity of causal relationship challenges our understanding of system behavior. So it's difficult to say, okay, I don't know, there is fluctuation because of delayed feedback there. So that simple way of finding candidate explanations that for system behavior that I was illustrating, they are not easy to implement when the complexity of the system is challenging. Okay, so it's not so easy to understand the system. It is therefore not easy to predict it or control it. Okay, so that's the idea. So how do we cope with complexity? Now, Ferenc Jordan, a colleague working with network representation and complex system representation, food webs, and so forth, he provided 3 simple heuristics. That's what most scientists would do, and most decision makers would also do. You start with a very complicated situation, and then there are 3 options you have. One possibility is to aggregate it. Okay? All those were seabirds, all those are sea mammals, all those are fish. Also, we're talking 80 species of fish. Make it into one box that are called fish. So these are functional groups or any type of grouping that takes into account shared properties of the members of the group. It's a viable option. And then I do my aggregation into boxes. I oversimplify often the system, and that's it. This is what ISIS did in that ecosystem overview. So they simplified very much the system, and then they show us causal pathways that may run through. In fact, in that case, we're looking at possible causal pathways impacting the different components. Let's say seabirds, sea mammals, fish, and betas. Okay, that's one option. The other option is to take a subset. So, for example, in ecology, if we are looking at food webs, we could focus on 2 trophic levels and say, I'm only interested in the in some predators like piscivores and the fish prey. Okay, so we extract one sub component of the system and focus on that. Okay, so I analyze what is called, in this case, if we have 2 layers in a network, we're talking about a bipartite network representation. I analyze that. It's a simpler problem than looking into the full complexity of the system. And then I need typically to do that for either target species that I'm interested in or target components I'm interested in. I might need to complement that with another subset and so forth. And then the third option is to identify important nodes, so important components, which have a very, let's say, strong influence on the behavior of the system. So identify the important components and extract those from the very complex representation, extract those super important nodes or components of the system and their links. So they're connected components in the system. This is the much simplified subset of the original system that emphasizes the importance of certain individual components of the system. Okay, code for the Barents Sea, for example, code would make it into such a representation because it has very many predators and prey, and it has a strong ecological influence on the Barents Sea, and it has an important socioeconomic role to play. So code would be probably one of the thick nodes here. Okay, this type of representation. Okay, so 3 options that we have. These are approaches, heuristic, simplified ways of addressing the system. We have, for the Barents Sea, for example, we have done something like that. We have simplified from the many thousands of species in the Barents Sea. We have gone into a few hundred, so 250 species. There are already 2,600 links between them. So things are rather complicated. That's for the entire Barents Sea. But then we could split in space, so look into different areas of the Barents Sea, which have subset of species. So we simplified a bit, food webs, and then aggregate. Once we have that sort of mapping of the food webs in the system, we aggregate and further simplify the networks, and then we include the perturbations for human activities that are relevant and that target different system components. Okay, so we could have, let's say, the harvesting, oil and gas, climate effects, and so on. So this is done in a recent paper published this summer. And once we had that simplification, we could apply loop analysis to the aggregate system. So first, we mapped the variability in the system structure, so in the food webs, in this case, the ecological part. Then we aggregate and simplify those structures. Okay, we look at what type of perturbations they experience in different areas in the Barents Sea. And then we further simplify the analysis for the loop analysis, qualitative approach. So this is primarily qualitative. Okay, it does provide insights, but we may be mistaken when we aggregate, when we simplify. So the exception, so all those layers of decisions need to be informed. So these are iterative processes. We need to revisit this again and again and check that the type of simplification we made are appropriate. But then once that work is done, we can gain insights as to, for example, relevant management decisions that may be made for the Barents Sea. So that's an example of how those heuristics we were discussing can be implemented. And once we have a simplified system, you can apply loop analysis, formal tools that can simplify the complexity of the, let's say, the analytic part, okay, the system behavior type of analysis. Okay, so we conclude now, just the last couple of slides. We see that there is a need to help us when the system becomes sufficiently complex. We need tools, okay? I mentioned some, for example, through network analysis, we can simplify representations, we can extract properties of networks that help us make decisions and understand them. But social ecological systems that are relevant to management decisions typically are complex. So this interrelation of system components generate cross-sectors trade-offs and may give rise to areal conflicts. So we need to address the trade-offs in light of the system representation, so system understanding. System thinking helps to cope with the complexity and can be supported by dedicated tools. Here are a few examples of tools that can help us in system thinking. Network analysis we have illustrated. The simple qualitative models and the loop analysis we have illustrated just to give some idea. Venn diagrams, you might have heard, these are just simple probabilistic type of representations. Bayesian networks and other causal graph type of models can use data, can use expert knowledge, for example, with Bayesian belief networks to reconstruct simplified representation of a system and then see what implications of given decisions might be. So they can do counterfactual. You can see if I increase the fishery or I remove the oil and gas extraction here, what would be the effects, okay? And then we can complement, so essentially complement these type of approaches with trend analysis, looking at the trends in the code numbers, Kepler numbers, and so forth, and can check whether the insights we have gained about implication of a given intervention actually are realized. So by looking at the behavior of the system over time, so doing adaptive management, essentially tracking the changes in the system in response to what we decide to do, whether the response of the system are in line with what we expect, or let's say, surprising stuff. Okay. Now, all these type of approaches assume that, for example, the ecological system stays the same. So there is a given structure to the food web, for example, and that the system stays the same. And then based on that, I can make predictions, and then I can track over time the changes that take place. What is very challenging nowadays with regard to sustainability and decision-making is that due to climate change, we see changes in food web that are taking place at the same pace of the impact of decisions made by humans. So essentially, you change management regime in an area, and climate change within 10 to 20 years is changing at the same time the structure of the system itself, so the causal structure of the ecological system. So you no longer know whether the impact is due to human intervention, climate change, a combination, what's going on, right? So some of the things I've introduced, for example, focus on equilibrium, behavior, and so on, need to be taken with some caution because the system is in transition. So the ecological system is in transition at the moment. Okay. Okay. So that's word of caution. Fine. Then these are just examples. So the trend analysis just follow the different components over time, their properties, how things are changing. These are just simple diagram representation of cause-effect relationship, and then this can be pulled together into causal loop diagram that can look back into the trend analysis and communicate, essentially. So I have a given expectation and I test it over time, okay, if things are behaving accordingly, and then I can move into what I call system archetypes. These are representation that I can connect to all the previous, for example, insights from system thinking. Okay, here's a list, one of many you find on the internet about good practice, okay, on system thinking. We touched on many of these issues already, so you will recognize some of the sort of suggestions about what I should take care when I'm dealing with systems and complex systems. And so I hope this has been useful. So what we have done up to now is really a gentle introduction to system, but we already gone all the way to complex systems. Balancing, I can promise, is not the simplest of systems to manage, to understand, to predict. Okay, so I hope this was useful. If you have comments or questions, we can take it also over the email later. I'll place the slides on Canvas, so you have them today. Any comments or questions up to now? Please. Yeah. Yes. So what was done? Okay, so just to simplify. Okay, so this type of approaches, what we do in these cases, we know that there is spatial variability in the species found in the Barents Sea. Okay, so we know that it's not true that every species is meeting everybody else in the Barents Sea. There is some spatial structure. That's why we had to do this spatial simplification. So the first thing was, okay, what would be a sufficiently coarse, so spatial subdivision of the Barents Sea that respects the variability in food web structure? So which species connect in what way? Okay, so to get there, there was quite some effort. We knew that the Barents Sea is separated into a Arctic water mass with Arctic species and a Atlantic water mass with boreal species. So there was a zoogeographic separation of the Barents Sea that simplifies, that helps find that line of separation. And then when we look into food web together with former students of mine, so Susanne Koch, Laurent Perpouche, Marianne, so all the people that have done such a huge effort on the food webs in this area, we found that there were similarities in food web structure in different areas. For example, in the Southwest, these were similar, so they could be aggregated, clustered into one representation. Okay, so I had a higher resolution in space of small food webs all over the places, and then statistically, and then through network analysis, we could find similarities, and I could combine them into one representation. And then one representation for the Southeast, one for this very Arctic cold area, and then the Northwest. Okay, so these were Arctic dominated with certain peculiar properties we found, and then these were more boreal species dominated areas. That was the first step. Okay, so we had a large food web, and then it was spatially, so the different species were placed in the right place with the respective links. And once we had simplified that, we needed one further step. So after an analysis of the networks for this area, we needed a further step to aggregate what were, there were something like 120 different species here. Okay, we needed to aggregate that to say 20 nodes. And this aggregation was done through a new method, a new approach for this particular paper. In the past, you would aggregate species by similarities. For example, if two species have the same prey and predator, I put them together, okay, in a trophy species. But this, in this case, things were a bit more complicated, so we needed to simplify quite a lot, aggregate a lot. So what we needed was a method that could ensure that the aggregate, so the behavior, okay, the dynamic behavior of the aggregate network respected what you would expect from the more complex system. Okay, that was the new step that was done in this paper. But the idea is the same. So you simplify. You can do it based on biological intuition, which are similar species. You can do it with network tools and so on. You simplify, and then you look at what are the perturbations. So in this area, do I have fishing, harvesting? Not really. Okay. Do I have harvesting here? Yes. Then harvesting comes in here, but not here as a perturbation. And then climate change, we know, is affecting very quickly the properties in this Arctic sector. So ice is lost and so on. So we had climate affecting some of the ice-dependent species and the colder, also less tolerant species for water temperature and so on. And then we added some other perturbations from trawling, for example. And when that was done, we could look into the qualitative loop analysis for each of those small members of the system. Okay, and yes, and then the next step to have the overall picture is that you need to look at connectivity, so species that eventually might connect the parts. Okay, and so you get the full Barents Sea perspective. Okay, that's so it's doable. Okay, so it's not beyond hope, but that's a simplification represented. So we cannot take it as the final answer. It's just one step towards that insight. Okay. All right, then I think we used our time. Thank you very much, and good luck with the course.